The noise from the cascode device can be reviewed as in the slide. So if you calculate the input reference noise voltage, you will get this equation. One thing that is noted is that there is no contribution from the M2. M2 will have a finite GM2, but it doesn't show up in the input reference noise. Why is that? So one intuitive explanation like this. For example, if you have a noise from the cascode device IN2, this noise current can be referred to the gate by let's say to the gate. Its voltage level will be IN2 square divided by what, GM2 square. That would be what, 4KT gamma GM2. Now you can find out the gain from this noise voltage source to the output. As you can see, the bottom transistor is current source. Its output impedance is infinity, right? So if you assume that R out is large, then the gain from the output from input, so Vn2, so V out over Vn2 would be what? That the gain AV would be GM times minus GM times RD, GM2 times RD divided by 1 plus GM 2 times RO, right? Since this RO is infinity, this gain becomes 0. So no noise contribution coming out of this gate noise voltage source. So there is no noise contribution from the cascode device. So thing is that the other way to explain this is that even though there's a noise voltage moving up and down, and this is like a source follower from gate to source, so moving up and down, even though this source node is moving up and down together with gate, meaning same VGS is maintained, and there's no current variation on this branch because the bottom is current source. This bottom device set the branch current ID, large signal current ID, that is fixed, and that means the ID times RD voltage drop is always there, so regardless of the noise amount out of M2. This is something that you can consider in the cascode device. Obviously, if there is some finite impedance on the bottom in the current source, then we have some noise contribution. Output noise is observed, right? Let's also review the noise in the current meter. Let's say, for example, we have a current meter shown in here. Then there is noise from the M reference device, that is diode connected device there. If there's noise there, it would change the voltage, right? If you want to find out the voltage at the gate, would be what? Vn equal to In times what? 1 over Gm impedance from that MREF device. if there is any voltage fluctuation here, then the M1 current will be modulated, so there becomes a noise current on top of the M1 noise itself, right? And one. So to remove the noise from the MREF, we put a very large capacitor there, so the noise voltage is reduced by lowering the impedance. So overall impedance on that node would be 1 over GM in parallel with the 1 over SCB. Right? That's square, right? So this noise voltage shown on the node X will be reduced. The other way to reduce the noise contribution from the MREF device is putting a RB, large register. So this forms a low pass filter, LPF. Without having RB, the bandwidth is limited by GM of the MREF device and C. So if you wanna have a very high bandwidth, a low bandwidth to filter out the noise, right? So we know that noise is flicker noise and thermal noise. We want to cut it out by passing low pass filtering, like this. But having low bandwidth require either large capacitor or large resistor. So having large resistor out of a 1 over GM, the diode connect is very limited. So we usually put a large resistor there. This resistor will reduce the bandwidth, noise bandwidth. The noise voltage shown up in here will be attenuated. So finally, the clean the bias voltage will be generated. This large RB, so large RB limit noise bandwidth, right? But to having a large RB in polysilicon require large area. So there's other technique to implement the large resistor is that use the triode transistor. So this is a triode region. To guarantee that triode, we have a voltage drop between drain and source is less than VD set. This is true because there is no DC current. IDC equals 0. So in DC there is a 0 voltage drop. So this is the triode region, and we can have a small overdrive. So this is overdrive VTH plus overdrive. If you can design or provide the voltage to have this overdrive voltage is small, because our own resistance it would be 1 over mu n COX W over L times overdrive voltage. So if you have a small overdrive, it will be good. So having small overdrive, so it must be guaranteed the VGS of this MR transistor must be greater than VTH. To ensure that we are cascoding the diode connect device MC, that will definitely there's non-zero current through MC, meaning it set up the overdrive voltage, right? So VGS equal VTH plus V overdrive voltage there. So by sizing MC large size will reduce the overdrive voltage, right? Such overdrive voltage is applied to the MR, right? So this is a very the handy circuit to track the VTH variation. If the VTH vary for all devices similarly, then we can guarantee that the constant finite overdrive or desired overdrive is pretty well maintained, right? This is one way to implement a large register using the triode. So MC is large, so large MC and small MR device, so W over L, right? That would give us the proper range of the register. Okay. In this slide, we will see how we size the device so that we can have a lower noise out of a current meter or current source. As you can see, all the noise contribution typically out of a current meter is shown here. The incoming current source has the noise, and we have a diode connected device, and we have the noise from that, and also actual current source, we have a noise there. So we know that noise from the current source is 4 kT gamma here. Gamma is 2 over 3 over 2 over 3, and 4 kT GM gamma 4 kT GM is the noise from the current source. Now, as you can see, to minimize the output noise current, obviously just by looking at this single transistor, we have to have a small GM for the given I current, meaning GM equal what? 2I over V overdrive. So we have to minimize the overdrive. So how we minimize the overdrive? So for the given current, have mu n COX W over L V overdrive square. For the fixed current, if you want to reduce that, then reduce the we have to increase the overdrive so that we have a smaller GM. So if we increase that, inevitably, right? If the overdrive goes up, that means the W over L must be goes down. So we have to have a small device on the current meter. But if you make it too small, then flicker noise become large. So we have to make it like N times W over N times L. So we have to size up, we have to increase the area, large area for less flicker noise. So small W over L, a small V overdrive, so less thermal noise, and large area, N times W, N times L, less flicker noise. Okay, so far it is so simple result that we are seeing. Now let's take a look at the source degenerated current source. In that case, what would be the noise contribution and how we reduce the noise. In the previous example, what we had to do was for lower noise, we had to have a small GM on the current source. Then if we have a degeneration register there, effective GM, the big GM will be degraded, as you can imagine. Big GM was what? GM over 1 plus the GM RS. So having large big GM, you will get the equivalently less noise at the output, right? So smaller big GM, less noise at output, right? But you are adding the register noise contribution out of like this. So we have to find out the noise contribution from input device, the transistor is large, or the from the register is large. We have to decide which one will dominate, which will be large. For exercise, let's calculate the noise contribution out of for the source generated amplifier, the current source. In this case, we have a two noise source, either current source, transistor noise, and the register noise. So you can calculate the output noise current in out by using this. You can make like what the output connected to ground and something like that. In this case, it would be much easier for calculating noise in terms using the voltage equivalent model here, right? So we are and in this case we can calculate the big GM easily out of this, right? So for the VN1, so output IN out equal what? So from Vn to output is what? So Vn square times the gain is what? So G and transconductance, big GM is GM1 plus GMR, right? That is gonna be transconductance, and plus what? So we have R there from voltage gain from input voltage to output what the current for this kind of the case is that what so first we have to find out the register division. So Vx node voltage would be what? So VR square times the R plus 1 over Gm times 1 over Gm square. That would be Vx node voltage square, right? And then from here to output is what? The transconductance now is Gm, right? So finally we found that the output noise current by equation. So what we'll have is a Vn square is 4kT gamma Gm. 4kT gamma over Gm times Gm over 1 plus Gm R square plus VR is what? Noise voltage from the register is 4 kT R times what? So Gm 1 plus Gm R square times Gm square, right? So you have the final equation like this, and you can make it simplify, right? We have a common factor here, so this guy and 4kT, right? So I will leave the simplification for you, and so you can take some practice. Okay. On the right hand side, we have plotted noise contribution at the output, either from transistor in blue or the register noise as we increase the source resistance. So in this case, we have R1 and R2 the same, and we increase from 0. If we put a 0 source register there, we have just a 4kT gamma GM noise at the output. So if as we increase the R, the noise contribution from the R become large, and at some point 1 over GM, it goes down, right? So as you can see, overall noise contribution at this range, the overall noise goes down. So if you have a large register there, overall output noise can go down. But the issue is that large R require finite DC voltage drop at bias, right? Meaning the minimum voltage at the drain is limited. It will be quite large because we have to consider that the VR. So this is only useful for the large supply, high supply application where the signal headroom is not a problem. So we can, in this case, so having source register can reduce the noise, but obviously reduce the voltage headroom at the output, right? Now let's go back to this example. So now we know that the having large source register will less noise, but for the given supply and headroom, for example, so we apply the same gate voltage so that the output drain can go down up to what? So the minimum VD minimum drain voltage VD min would be what? VG minus VTH, to make sure that all these are in the saturation region, right? So having this requirement sharing for those two transistors, same requirement there, then what would be better result out for in terms of the less noise? So if you want to have for the same amount of current, we have to reduce the W over L of the M1. For the same gate voltage and for the same current level, we have to have for the M2, we have to have a larger device, so meaning less overdrive. So on the M1, need to have a large overdrive and smaller device size. For the M2, it should be a less overdrive and large device size to flow the same amount of a current, right? Now in this case, what would be the noise output result? The result is that for those cases, for the given gate voltage fixed and sharing, in that case, either M1 or M2 has the same, both cases have the same amount of output noise. So there is no distinction, no advantage of having R. You can think of this as for the let's say you can think of this problem, this issue or consideration as follows. So let's say if you have a device W over L, if you want to make it small, one way is to cascade the device like this, W over L and W over L. Obviously the bottom transistor will be in triode region. This is the saturation. So in triode region, it is equivalent to what? It's just equivalent to resistor R on, right? So basically in CMOS technology, having the same gate voltage, just by different sizing, that would result in the same noise amount of current, okay? Having this kind of register, source register below the transistor to reduce the noise is popularly used in BJT. This technique was used to BJT because the BJT GM is very large. As you can imagine, GM is I over VT, right? So its noise is like the shunt noise current we have 2QI the noise. So to degenerate the GM, we had to have a R there in the BJT. So BJT having emitter R resulting in less noise. In CMOS device, there's the freedom of choosing different L and W, right? But in the BJT, they have the only choice of having just a device size. There's no mechanism to control the overdrive voltage. It just always have a follows just a diode exponential curve relationship. So in the CMOS technology, having R is not popularly used. So large R is just equivalent to having R. So okay. In terms of the noise, let's look at the noise in the differential pair. As you can see here, differential pair construction like this. So input reference noise should be the voltage source and current source between those two terminals. If you calculate the input reference noise source, we have a factor of 8. That is 2x larger than the single-ended, 2x larger noise voltage, right? Density. And here in the flicker noise and also the thermal noise, but our signal range is even 2x larger in this case, even though the signal power is 4 times larger compared to the single-ended case, because we are driving positive and negative, right? Opposite polarity of the signal. For example, if your signal amplitude is A in the single-ended, and differential sense, we are driving 2x larger, much larger signal swing here, right? Like this, right? This is a 2A amplitude, so 2x larger differential amplitude. And compared to single-ended version. Right? So in terms of SNR, it's better, right? 3D better. Let's show you how we calculate the noise voltage one by one. So all the noise sources will be presented here as shown in here in the diagram for register noise and the device transistor noise. Once we have this, anyway, we have to refer to the input. So this noise and this current source, this transistor noise can be referred to the input noise voltage easily, right? So if we use the GM square, so divide this one would be what? IN square divided by GM square. So we can easily refer to the input gate. Now do we have to refer this noise noise current from the RD to the input, right? If we know the what if we, let's say if we use that the output noise current, it will be much easier. If you short the output to ground, this noise will, all the noise current will flow out to this shorted connection. So once we know the big GM, we can already easily refer to the input, right? How we refer that? So that IN out, so on IN R will be referred to the input by what? Big GM. Here the big GM of the circuit will be what? Just GM2, right? So adding this noise and that noise will be the input reference noise. And then we have another noise from the left hand side. So we have a total 4 noises will be added, right? So then that will be this equation. And also we need to take into account the flicker noise similarly from the input device. So this is the way how we get this input reference noise voltage rather than the input rather than the current noise from the device. So we can just use direct derivation of the input noise voltage here, right? And also for the output noise register, noise from the register, we can also use noise voltage rather than the current. Once we know the noise voltage there, the output noise what will be directly shown this level, shown by that level. But if we want to refer to the input, we have to divide that noise voltage, output noise voltage, by what? AV square, voltage gain square, right? So here voltage gain, so output noise would be what? 4kT in gamma and 4kT RD divided, gain is what? GM times RD square, so 4kT GM square RD. So this is the one side of the RD noise from the RD. So the final noise from on the right hand side only will be what? 4kT gamma over GM plus 1 over GM square RD. But there is also noise from the left hand side, so we have to make it times 2. So this part comes out like that. Let's think about the noise and power trade-off. For example, for the common source amplifier, we know that input reference noise voltage would be what? Vn would be 4kT gamma over GM plus noise from the RD, that would be 4k noise voltage is 4kTr, right, divided by the input gain, so GM square times RD square, right? So in this case, having a large GM, we know that it would be smaller input reference noise. So once you designed your amplifier to satisfy certain gain, required gain, that is AV is what? GM times RD. Once that is designed, to satisfy certain noise requirement, you have to raise GM. But once you change your GM, you will get the different gain. So to maintain your voltage gain, what you have to do is that increase the GM by sizing up W, and also that must increase the current so that the output common mode voltage doesn't change. And also the resistor should be half. so that the overall gain would be the same, right? So GM is 2x larger and the register is 2x lower, so overall gain is still GMRD, like this. So now the GM is 2x larger according to this equation, right? So we have our RD factor here. So having large GM and having large GM would be a smaller noise, but in order to have a same gain, I mean same voltage and same gain and voltage, it is inevitable to have the smaller output register. So that will result in a little higher, but overall GM is much faster, GM grows much faster than the RLD, so overall noise becomes small. So how we maintain input bias voltage and the output bias voltage and the without altering the gain, as we have shown here. So everything should be 2x large. Everything should be 2x larger than before. So you can look at this modification as a different point of view shown in here. So basically, if you design the one device like one amplifier stage, you put a same stage in parallel like this, and then connect the input and an output. So this will directly corresponds to the left hand side, the circuit. So having multiple device, like a scaling amplifier, can the scaling up the amplifier reduce the noise, input reference noise voltage, noise current voltage, reduce the noise. One thing that people or students confuse easily is that here the register, if you scale up the amplifier, your load register becomes the smaller because the register is connected in parallel, right? For the transistor, your GM just grow as you scale up your amplifier, right? And also current is scaling up as you increase your amplifier. So in your actual layout for unit device like a resistor and transistor side in here, if you make it scale up, so wider device and wider resistor, and then more current flows, right? Some things like that. So here, this is for summary. So we have, if you have a track larger, the scaling is there. If scaling happen, then we have the tracks lower thermal and flicker noise. Why tracks larger? For example, we have for the input device only. So here we have the different factor GM squared. But typically, if we have a typical amplifier, if you have a track larger GM, right? Track larger GM, then you get the lower thermal noise. But and also, if you have a larger device like if you put a larger area, so we have a track larger area, then the area, so W times L, will be doubled, 2W and 2L. So area becomes 4 times the larger, right? I'm sorry. So area is 2 times larger. So W becomes, let's say in this example, W gets the 2x larger. So in this case, the flicker noise power becomes 2x larger area results in 2x lower noise voltage. if you remember, the flicker noise equation is what? Input reference noise voltage density would be what? K times COX W times L and over 1 over F, right? So having tracks larger, we have tracks lower noise power. So this tracks larger scaling up is equivalent to 2 instances in parallel, so that results in tracks lower noise power. The problem is, but this is the power level. So if you convert that into actual voltage, noise RMS voltage, then it becomes the square root of 2 lower RMS noise will be there, right? So in general, the case, so you have a 2 amplifier, they connect the input and an output together to construct the input voltage and output voltage. Then overall noise power becomes half, because so each block will have its own input reference noise voltage, and here, right? If you tie the output here, then what you have is that the noise voltage contribution to the output would be what? 1/4 of the original amplifier of itself noise contribution. Why? Because the output load impedance becomes G out becomes half, right? Because we have a parallel connection at the output. So this factor gives us the 4x lower the noise contribution for each output. Overall, the noise voltage at the output you see is the 2x lower noise power. Okay. So when you consider the converting noise spectral density to the actual RMS noise, we have to integrate the noise power over frequency. So we have the density, noise density plot here. If you want to change and convert that to actual RMS voltage, we have to integrate all the noise on the this noise curve plot. So that corresponds to like this. That becomes the Vn times RMS voltage, right? Scale. So we can find out the RMS voltage. So in a typical, most of the case, actual amplifier bandwidth is defined by multiple poles at the output, multiple RC network. So we can define the noise bandwidth that so noise bandwidth Bn, noise bandwidth is Bn defined like the same noise like this, right? Definition. In a multiple pole system, overall integrating noise power is equal to square brick wall case. So starting from the low frequency noise density, we extended this flat. So this is the brick wall, like a square, like a rectangular. We assume that noise is white over this noise bandwidth window. So we calculate the noise power by this equation. Then we can calculate the equivalent, right, noise bandwidth, which satisfy which satisfies this equivalent equation. So what it means that if we find the noise bandwidth, then the outside of the noise bandwidth here we have a additional noise contribution here. This noise contribution is exactly the same as that the A1, right? In that way, we can find the equivalent noise bandwidth in Bn. This is the equation that we found. For example, for simple one-pole network, one-pole low-pass filter, we have like this. So omega p, right? So what would be noise bandwidth? So noise bandwidth is that what? So we have we had found that before, right? Noise bandwidth Bn is the frequency. Let's say in frequency you can say that either angular frequency or just frequency is defined. So the bandwidth would be what? The pole frequency times pi over 2. For the one pole low pass filter, we have this kind of a relationship. So that is approximately what? To around like 0.7 times. Oh, sorry. Something. Around what? Well, sorry. Pi is 3.14 something, right? So the FP is so a little bit higher than bandwidth, 3 dB low pass filter bandwidth we have, then the actual noise bandwidth is larger by this pi over 2 factor. So you can go back to the KT over C noise calculation slides, and there we have shown that that factor is pi over 2. Okay.